Hello and welcome to Technology Update. We're often on a bit of a different beat than our colleagues here in RT's newsroom. And while they work together to bring out today's breaking news, we're going into complete isolation to prep for the future of long-term space exploration.
If it takes 2 years round trip to get to Mars and back, could you stand the test? And where could you train for that kind of mission? At the end of an ominous corridor in the basement of a Siberian institute? They lock you in and throw away the key. Picture a cramped space, recycled air, recycled waste. There's no exit without mission failure, and mission failure is not an option. You sit in your cube and watch your only food grow slowly. You dream of the day you'll see solid ground, a sunny sky, or the people you love the most.
Okay, so it's not a nightmare. It's BIOS 3, the brainchild of scientists at the Institute of Biophysics in Krasnoyarsk. They started preparing the facility for habitation by crews of so-called bionauts back in 1965. Plant life was already an area of expertise for the Institute, and they were selected for the prestigious project by Sergei Korolev, widely acknowledged as the father of the Soviet space program. From the beginning, the idea was to create a manageable ecosystem to research the ability of people to live under basic but ecologically balanced and maximally self-sufficient conditions. The ultimate objective, establishing a scientific and technological foundation for long-term space travel, to the moon, to Mars, and perhaps beyond.
The experiment we're carrying out allows us to deepen our theoretical understanding of the link between man and his surrounding environment. We have constructed a world in miniature where people will live for 6 months, isolated from the greater world outside.
That little world consisted of 4 rooms totaling just 315 cubic meters. One room was living space, with berths for the bionauts and the only airlock for limited communication with the world outside. 2 rooms were devoted to plant cultivation, mostly regenerative crops like wheat and vegetables to keep the crew well fed. And the final room for growing the chlorella algae that helped regulate oxygen and CO2 levels in the experimental environment.
Now we're entering the room where the test crew lived in complete isolation for half a year. This is the living module where they worked and rested. There were 3 individual berths where they could spend some time on their own. A bathroom with a shower. This module also housed the equipment to regulate the regeneration processes of the BIOS 3 environment from the inside.
While the bionauts set about their work within the complex's walls, there was plenty more to be done on the outside. This was no Siberian survivor. The BIOS project was backed by the Soviet government with $40 million in today's money, as its initiators expected results valuable to the future of space exploration. The amount of oxygen in the chlorella-driven regeneration system was monitored closely, completing a full cycle every 53 days. The team inside participated in and self-administered testing, passing data to the outside for analysis. They gave regular blood samples, strapped into monitoring devices even while sleeping, and followed instructions from the experiment's directors at all hours of the day. Intercom contact was maintained at all times. Peak performance was achieved in 1972 and 73 when the longest-lasting live-in crew spent 180 days inside. Overall, the system hosted nearly 2 decades of manned experiments and 3 decades of ecological testing. An amazing volume of unprecedented work.
Now we're in the regeneration module. That's where the bionauts got their food, oxygen and water. It's basically a greenhouse for higher plants that were grown on a special substrate of serum sites. It's kind of construction material, very porous and capable of holding moisture inside, so that the plant's roots could do without water for a long time.
Plant growth was in many ways the lifeline of the BIOS experiments. Crops had to be carefully selected to produce the desired yield in the desired time frame, and exhaustively shielded from contaminants and negative biological interactions that might spoil output and ruin the project. The wheat bionauts raised literally put the bread on their table in the neighboring room, and other basic crops grew right alongside. Short of meat-derived fats and proteins, they succeeded in closing off roughly a third of their food production.
This part of the facility helps you understand how the system's lighting worked. Lighting was a vital factor facilitating the process of photosynthesis. Without photosynthesis, there would be no oxygen or food. Our choice at the time was xenon lamps. They produce a sufficient amount of light and are ecologically clean with no ill effects. Thanks to its numerous benefits, the xenon lamp remains a key element for the life support system. We can't just swap it for something else. Before the shift, we must pick a new source of lighting, which is not a trivial task. But that's one we're working on at the moment.
That's just one of many modernizing tasks underway at the facility today. With the Russian economy recovering from the Soviet Union's collapse and a renaissance in European interest in the unique Krasnoyarsk know-how, the lights are turning back on at BIOS.
Now we're going to the modernized regeneration module for the production of food, oxygen and water. With financial support from the Siberian branch of the Russian Academy of Sciences and the European Space Agency, we're upgrading the system. Among the problems to be solved are the increased irradiation generated by new, more powerful sources of light, which we need to intensify oxygen generation, plant growth, and transpiration of water. Also, there's a network of sensors that help us keep track of the process from the main control room. We can now monitor the interior and check the system parameters. We can also electronically transmit all these data, not just to our scientists here, but to any other research institution either elsewhere in Russia or abroad.
That information is of particular interest to a Barcelona-based project under the auspices of the European Space Agency. Its nicknamed Melissa, the so-called microecological life support alternative, hopes to use the right mix of plants and bacteria to help relieve medium and long-range space missions of at least some of their hefty supply load.
In the frames of my postdoctoral research, I spent 1.5 years in Barcelona. And I was involved in the first investigations on the higher plant chamber compartment. And for the moment, they are doing this in different universities that are partners of Melissa project in different countries. They are going to use as a crew only rats. They are not allowed for the moment to include humans inside. Here, for example, in Institute of Biophysics, we have a very big experience, and we had experiments with the humans inside for 6 months. So for Europe, it's still only the beginning. So for them, it's very interesting to know which problems we had, which achievements we had. So it's a very interesting experience for them.
By the Europeans' math, 40 rats account for a similar oxygen intake to that of one astronaut. The rats are now being tested in a system designed to produce 100% of their oxygen and 20% of their food.
It's going to be something like a biogenerative life support system for going to the other planets like Mars or Moon. And also they have some possibility to use some of the compartments for the flight, not only on the station, but also during the flight they can use this. And it's the aim is to recycle everything inside the system that a human can survive inside without addition of any food, water, and oxygen, and so on.
So far, all human space exploration has stayed within the Earth's orbit and been predominantly supplied from home. But specialists agree that to reach the Red Planet with the manned mission, the crew will need to be accompanied by biological systems. The longer and more complicated the mission, the bigger the ecosystem will have to pack with us.
1 hour, 11 minutes in solitary confinement, starting to feel effects of isolation. Okay, so thanks to you, I'm not totally alone. but we're learning there's a serious psychological component that has to be considered.
There's been a drastic change in my condition. I feel totally weak, no desire to move, don't feel like doing anything. My dreams have turned to nightmares.
I dreamt of a giant black cat jumping on my chest. I tried to tie it up, but it breaks away and attacks me again. I try to strangle it, still it escapes. A very dreadful dream. I woke up in a cold sweat.
So I'm not the only one driven a bit batty by these experiments in enforced enclosure. Moscow's Institute of Biomedical Problems, IMBP, set up a closed system running parallel to BIOS in the 1960s, only with total space cut down to 24 cubic meters and various extreme conditions introduced to stretch the participants to near breaking point. They also raised the bar on the length of the project. 3 participants spent the whole year from November 1967 to 1968 inside. The 3 men were eventually allowed into a small adjoining greenhouse, but there was far less emphasis on self-sustenance. The squad was specially selected to include 1 biologist to tend the plant life, 1 engineer to handle technical equipment, and 1 doctor to keep them all healthy. Concerns about oxygen and CO2 levels in the closet-sized cabin led the crew to rotate their stacked bunks every 10 days to spread out the negative effects of sleeping on the bottom. There was never enough food, but the men worked hard to stay healthy, and they are happy to emerge at the end.
The key difference between the experiments at the Institute of Biophysics and the ones here at the IMBP is their size. Here, the researchers focused on the study of the life support system for a spaceship. That's why the closed space was a small one. The core link in the oxygen production cycle was an autotrophic unicellular algae called chlorella. The Institute hosted 6 experiments, lasting from 1 to 2 months, with individuals living in sealed environments.
Chlorella was the same species used in BIOS 3's algal cultivator, chosen because of its phenomenal photosynthetic performance. Its daily oxygen output has been measured at some 100 times its volume, so a small stash made breathing easy, but further tests showed it could not be digested as human food.
Both the BIOS 3 and the experiments at our institute are unique. Basically, no laboratory in the world has been able to replicate them.
Now in the 21st century, IMBP has another unique set of experiments up its sleeve. Meet Mars 500, a string of increasingly long simulations of various segments of and now the entire trip to the Red Planet. The first of 3 planned parts to the ground-based project kicked off in 2007, at first with solely Russian participation. After the success of that short 14-day test run in these modules, 2009's 105-day Phase 2 had the full attention of space agencies and researchers from around the globe, as well as the participation of French and German crew members. The crowning accomplishment of the experiment was always intended to be the 520-day full simulation of the Flight 2 landing on and return from Mars. Mars 500 has 4 modules totaling 550 cubic meters. The largest is mostly for storage of dry and refrigerated foodstuffs, but also has greenhouse space and exercise equipment. Another is specially designed for medical and scientific experiments. Both of these connect to the main module with berths for the 6 participants, the central control room, kitchen, and common spaces. From here, 3 crew members will pass into the landing module for simulated descent to the Red Planet. In addition to the spaceship, the facility includes a 1,200 cubic meter space modeled after Mars' surface, where the landing crew will test a new Mars rover.
There are many challenges to just seeing these people every day, the same faces, other than yours on the mirror, in a locked space for 1.5 years. That itself is very tough, but it's a nice, interesting challenge.
The team has a Russian commander, surgeon and physiologist, French and Italian engineers, and a Chinese professional astronaut. For better or for worse, they'll spend the next 17 months in each other's close company. When the hatch was sealed behind them on June 3, 2010, they were off on the world's first full-length Mars flight simulation. Of course, they may feel miles away, but they're being observed from the command center. Unlike the BIOS experiments, Mars 500 simulates the communication delay associated with distance-based flight. A message and response takes 40 minutes. Sealed inside, they're keeping some of their focus on work, but also trying to enjoy themselves. The Mars 500 team runs a beta version of the regenerative life support system. Cosmonauts and astronauts need inputs of water and fresh air to survive, but they also produce waste, including solid waste, urine, impure water, impure air, and CO2. Everything apart from solid waste can be recycled into the system. Urine and impure water are processed to become a potable resource again, the contaminant particles are filtered and air returns into the ventilation system, CO2 could be broken down to generate water, and water to provide oxygen. 3 of the crew members will encounter a simulated version of a life support system at the beginning of February, when they enter this landing module to prepare for a Valentine's Day touchdown. For now, they're on the other side of a sealed hatch, and final preparations to the Mars landing vehicle mock-up are still in process, so we get a last-minute chance to peek inside and see what awaits them. In addition to assuring a safe set-down on Mars' make-believe red rocks, here they'll be in charge of regulating the vital settings of their own environment, while the control room throws up a series of potential failures and warnings within the system.
This is the main screen of the life support system, reflecting all the characteristics of the closed environment. We can use the software to simulate any emergency condition. It could be a valve failure, a fire aboard the ship, or a loss of airframe integrity. The system immediately sends a voice command to inform the crew of the emergency situation and the need to handle it. The system will help the crew to track down and solve the issue in automatic mode. At least, the life support systems that will be mounted on future Mars mission spaceships will not require any manual operations.
Part of that future is already in use on mankind's biggest outer space achievement to date, the International Space Station. Now in orbit with humans on board for more than 10 years, the massive satellite has been the base for testing a whole generation of new space equipment, including regenerative support systems.
The International Space Station uses oxygen generation equipment called Electron VM. Initially, its lifespan was set to be about a year, 365 days. But thanks to its reliable operation, it was decided to use the device on board as long as it could last. So far, it's worked successfully for 3 years, which means its lifetime is 3 times as long as we expected.
But what are they doing to make sure us needy humans last that long up there? Space shampoo, named Aelita after a Russian sci-fi novel, microgravity tested, and no water needed. So what do you say? Bath time?
Aelita is produced in a special laboratory in the same Institute of Biomedical Problems that plays host to Mars 500. And there's more than hair care on the minds and shopping lists of those heading to outer space. Hygiene in general needs an orbital overhaul given the specific constraints of life inside a microgravity bubble. No sinks, no showers, since water can't be trusted to go down a drain, and is certainly unwelcome floating around all the expensive equipment. Forget about potent scents and products containing alcohol, since you can't open the window to clear the air. Filling space explorers' toiletry bags is an altogether separate industry.
Институт медико-биологических проблем является фактически
The Institute of Biomedical Problems is the only medical center which develops and produces personal hygiene and cleaning products, especially for cosmonauts. Our wet towels have found truly widespread demand. They are saturated with a special lotion and are very easy to use. Also, we've got unique items not provided by our Western counterparts. A product that keeps your mouth clean and healthy, which is basically a gauze cap with an elixir to be placed on your finger or toothbrush. It's made only in Russia, but is popular among astronauts from around the world who order it quite often for their trips to the International Space Station.
What about eating on board? Shorter missions may allow for some typical comfort foods to come along, but if you really want to stay stocked, supplies have to be packed for the long haul. Astro and cosmonauts need the same nutrients, but it won't look like a steak or a salad from Earth. Chop up a normal apple of your favorite variety, mash it to bits with your handy food processor. Mix in some yogurty goop and stick it in the sublimation oven. Not gourmet enough for you? IMBP works alongside the University of Applied Biotechnology across town to whip up space specialties with the right nutrition balance for high-flying crews. As a method of preservation, freeze-drying food has been with us since the mid-20th century, made for all kinds of extreme or isolated conditions, not just for novelty gifts like space ice cream. What's different about this sublimation process is the inclusion of probiotics. That yogurty goop is a bacterial culture that gets mixed in with our apples and other provisions to help us obtain the proper dietary mix, keeping us healthy without the benefits of culinary diversity we're used to with earthly luxury. The taste? Well, not that bad either.
We're hoping to stage a joint experiment with the University of Applied Biotechnology to assess the performance of the next generation of probiotics. We will try to create dairy products based on autologous bacterial strains. To my knowledge, this will be the first experiment of this kind in the world.
What we're talking about here are tailor-made autoprobiotics. This new practice would grow your own individual bacterial strains and feed them back to you to maintain your healthy diet with no risk of allergy or rejection. With your digestive system supplemented by probiotics, you have other aspects of your physical well-being to worry about. Back at IMBP, we're making sure our muscles don't wither away in space, leaving astronauts and cosmonauts on a long road to post-flight recovery. On Earth, gravity's effects build us up by holding us down, maintaining basic body strength by giving us weight. That's all afloat in space, so IMBP and other researchers have to manufacture methods of combating the muscular atrophy and bone deterioration facing our space travelers.
If one of the problems with staying in space for a long time is not feeling yourself weighed down enough to get any muscle exercise, this is a pretty exaggerated solution.
But that's literally what it takes. Lacking gravity as a source of body-loading tension, exercise in space has to create artificial sources of resistance. Otherwise, ISS crew could pump massive iron without ever getting buff like Arnold. Specially made suits also provide an important passive method of mobility resistance, since space missions are high-precision operations with serious demands on the crew's time. This Penguin 3 suit developed at IMBP helps turn every minute into a bit of bodybuilding.
Starting from the early 1970s and until recently, we didn't have the means to measure the load weight of the suit. The rule of thumb for pulling up and tightening the rubber cords was the cosmonaut's own feelings. They had to move around comfortably and at the same time have some perceptible load weight.
Today's Penguin 3 is an evolved version of that earlier spacesuit, now with sensors offering the ability to control precisely the amount of force applied by the elastic cables as resistance against various muscle groups. The basic design has been preserved, allowing for passive and minimal activity toning on front and back, upper and lower body muscle sets.
We assumed that elderly people or people recovering from strokes could experience the same disruptions in physical activity as cosmonauts. And if we were able to achieve a positive effect when using suits for cosmonauts rehabilitation, we should get a similar effect with the disabled and the elderly. The results were astounding.
The need for physical rehabilitation these suits can provide is truly great, as Russia suffers one of the world's highest rates of stroke occurrence. But strokes are impacting ever younger demographics worldwide, meaning there are more survivors who need step-by-step assistance in regaining their physical strength.
Russia is the only country in the world that has come up with this treatment technique. We've been testing the suits for more than 5 years and have developed differentiated methods for various groups of movement disorders and for various groups of patients. We have success stories with full rehabilitation of mobility and mental ability after the use of the Regent suit. Patients were able to return to work and their families and enjoy the same life as before their stroke.
Based on the same principles, new technology is being extrapolated to help disabled patients in pre-ambulatory phases of their recovery process. Instruments stimulate the nerve endings in the feet that control our walking muscles, slowly reminding the brain what it takes. A new lease on life from extraterrestrial origins.
The struggle for survival and research in space is changing this world, even as it brings us to altogether new ones. And it might not make Mars seem any closer, but with the right focus, it won't be long till we're on our way. That's all for this month. Join us for more on the next technology update, if we manage to make it out of here to film it. And until then, enjoy the ride.